Okay. Oh, I see. It's recording. Okay. Okay. Thanks, Stefan. Thanks for inviting me. So this is a project that involves Lancaster University Management School and also the Land, Environment and Economics Policy Institute over in the business school here at Exeter. So before I before I talk about before I talk about prediction markets, I want to start by talking about three big problems that we think that prediction markets can address with regards to climate forecasting. So the first one is the sort of multidisciplinarity of the climate forecasting problem. Obviously, predicting climate, given a concentration of greenhouse gases, involves knowledge about atmospheric sciences, it involves knowledge about oceanography and other physical sciences. And that's just to be able to make a prediction that's conditioned on a particular concentration pathway. If you want to be able to make an unconditional forecast of climate, which you have to be able to do for things like adaptation and resilience planning, then you also need to take a view on the relative likelihood of those different concentration pathways. And that brings in a whole load of other expertise, like economics, social sciences, policy studies, what you think is going to happen with regard to technological innovation. So it's a very multidisciplinary problem, and we haven't really got to the bottom of how to manage that multidisciplinarity, that fragmentation of approaches, and also even fragmentation of modeling approaches. Now that we have things like AI and machine learning approaches joining more traditional modeling approaches like GCMs, how do you marry those together? How do you get the most out of all those different approaches? So the second issue is something economists call information asymmetry. With weather forecasting, short-range weather forecasting, if you're trying to sell me a short-range weather forecast 1 or 2 days ahead, you can produce a 1 or 2 year track record, and that is enough to provide a sort of statistically meaningful demonstration of competence. Now, when you get to seasonal time forecasting, so 6 months ahead, 1 year ahead, it becomes trickier to be able to provide a long enough track record to convince me that you know what you're doing. And when you get to long-range climate forecasting, you're predicting decades ahead, it is pretty much impractical for anyone to be able to produce a track record that says, I know what I'm doing. You might wonder why I've used some lemons to illustrate this problem of information asymmetry, and it's an allusion to a famous paper that was written by the American economist George Akerlof in the 1970s about information asymmetry called The Market for Lemons, because the example he used was the used car market, and in America, a lemon is a slang term for a dodgy used car. And he explained that when the buyers of used cars can't evaluate their quality, they're not prepared to pay above average prices because they can't verify that what they're getting will be of above average quality. So if you have an above average product, an above average used car, or an above average climate forecast, you will be reticent about selling into that market because it will be difficult for you to get fair value. So you withdraw from the market. And that, of course, reduces the average quality of what's left and reduces the buyer's willingness even more to pay top dollar. And a market can enter what is sometimes called the death spiral, downward spiraling of quality and a downward spiraling of prices, that leads to a market failure. And now that we have a sort of growing number of providers of long-range providers of climate analytics, especially in the private sector, a lot of companies now jumping in to provide long-range climate analytics products, it is useful to be aware that the market for climate information suffers from exactly the kind of vulnerability to market failure that that George Akerlof discussed in the 1970s. The third issue is something that has been called circularity in the context of inflation forecasting. So inflation forecasters have an issue because they want to try and forecast inflation, but inflation depends on the interest rates that are going to be set by the central bank, and the central bank takes into account inflation forecasts when setting those rates. And the same situation exists with climate forecasting, because climate forecasts are going to depend on greenhouse gas emissions and future concentrations, but they themselves will depend at least partly on policies to reduce concentrations, and those policies will at least partly depend on what forecasts are saying. So you have this interdependence between what the climate forecasts are saying and the policy that controls those forecasts, that controls emissions. Now, this issue is often sidestepped by producing physical climate forecasts that are conditioned on particular representative, concentration pathways. But as I mentioned, if you want to do adaptation planning or resilience planning, ultimately you need an unconditional forecast. You can't build your flood defenses conditioned on a particular pathway. You have to take a view, or somebody has to take a view, as to the relative likelihood of those pathways. Okay, so those are the problems that we think prediction markets can actually quite elegantly and simultaneously address. So now I'm going to start talking about prediction markets. So a prediction market looks a lot like a financial futures market or even a sports betting market. But unlike markets that are designed to allocate capital or to transfer ownership or to transfer risks, prediction markets are designed specifically to get information. Now, a lot of the existing prediction markets are structured around something called an Arrow-Debreu security, which is just a fancy economics jargon for a conditional IOU. So it's like a contract that says, I will pay you £1 if a particular event occurs. It's named after Kenneth Arrow and Gerard Debreu, who are economists. Kenneth Arrow, though, interestingly, was a meteorologist. He served as a meteorologist in the US Army Air Force during the Second World War. So these contracts, you've got these contracts. So for example, you have a contract that says, I will pay you £1 if the Democratic nominee wins the next presidential election. And that contract gets traded on an exchange. And under certain conditions, you can interpret the prevailing price of that contract as a probability or consensus probability that the event will occur. And so one of the earliest academic prediction markets was set up at the University of Iowa. It's called the Iowa Electronic Markets. And since the 1980s, they've been running these kinds of markets to predict elections. And this is from their website. This is the market that they're running for the next presidential election. And they have two contracts. The one that pays out $1 if the Democrat wins and one that pays out $1 if the Republican wins. And this is how the prices of those contracts have been evolving since about June. So you can see back in June, they were both quite close to 50 cents apiece, implying that it was a bit of a neck-and-neck race. But since then, the price of the Republican contract has gone down to about 25 cents, and the price of the Democratic contract has gone up to about 75 cents, implying that there's a 3-to-1. The Democrat is now currently the 3-to-1 favorite. So the Iowa electronic markets they're open to anyone, and they use real money. They have to restrict the number of people who participate for legal reasons. But other experiments with prediction markets have, instead of just allowing anyone to participate, they focused on recruiting experts. And one recent example of this was a prediction market of experts in psychology to predict whether particular psychological studies would replicate. Now, you might be aware or not that in some sciences, and particularly in psychology, there's something called the replication crisis, where a lot of famous studies, experimental studies, when they're redone, do not replicate. And there's a big reproducibility project now in experimental psychology looking at this. And this prediction market experiment was done as part of that project. So they looked at 44 different psychological studies, and they recruited experts to take part in a prediction market to predict that when they redid that study with a new experiment, redoing that experiment, whether they'd essentially get the same result. And they compared the results from a prediction market with the results from surveys where the participants in the survey, they were the same people. So it's the same people taking part in the survey and the same people taking part in the prediction market. And what they've found, so this is just graph from the paper, the red squares, the squares are the markets, the market prices. So they can be interpreted as the market consensus probability that the study would replicate. The ones that are red are the ones that ultimately did not replicate, and the ones that are black are the ones that ultimately did replicate. The circles are the same thing, showing the probabilities that they got from surveying the participants. And what they found is that the prediction markets were more effective and were better predictors of whether these studies would replicate than the surveys, even when the surveys were weighted by expertise. And as I stressed, the participants in both cases were the same. So this kind of study suggests that even when you're dealing with a particular group of participants or a particular group of experts, the prediction markets can aggregate their views more effectively than a straightforward survey.
Sorry, what was the explanation for this? Is it...
One explanation is the incentive. I mean, it's not a sort of proven explanation, but in the prediction markets, they weren't paying to play, but there was money that they could win. Not a huge amount of money because it was an experiment, but there is the argument that as soon as you start incentivizing people like that, then it sort of focuses their mind more than if they're doing a survey. And the other thing about a survey, of course, is sort of related, that giving your opinion in a survey is cheap, right? I ask you a question, you give me an answer. Whereas if you're taking part in these prediction markets and you have a pool of cash to spend, even if you've been given that cash, you will focus spending that cash in the markets or on the studies where you think you have an informational advantage. So you can effectively weight your confidence in a way that you can't with a survey. So it could be that those or a combination of factors like that led to the result. So people have been suggesting using prediction markets for climate for quite a while now. I think the calls for it go back more than 20 years. Quite a lot of legal scholars have suggested it. Economists have obviously suggested it because economists love a good market. Some climate scientists have advocated it as well. But they haven't really got traction for various reasons. There's various obstacles. One obstacle is called the liquidity problem. So back in 2011, a scientist, Mark Roulston, who was at Sandia National Labs, thought, just as an experiment, he'd set up a prediction market for the global temperature anomaly for the following year. So just going out from 2011 to 2012, just to scope out the problem. And he used the InTrade platform, which was a commercial prediction market platform that was operating out of Ireland. And what he did is he created a whole strip of these Arrow Debreu securities. So these are just contingent IOUs. So the top one would pay out $1 if the global temperature anomaly in 2012 was more than 0.3 degrees Celsius. And then the one underneath, exactly the same thing, but it pays out if it's more than 0.35 degrees Celsius, and so on, all the way up to more than 1.1 degrees Celsius. And on the InTrade prediction market platform, these contracts can be traded using what's called a continuous double-sided auction, which just means that you effectively have an auction of buyers and an auction of sellers. And to illustrate what that means, this bit here is called the order book, and it's the order book for this contract here that will pay out $1 if the anomaly is more than 0.55 degrees Celsius. People who want to buy this contract can put in bids, and people who want to sell this contract can put in what are called asks. And here what you're looking at is the highest bid, so there's 5 bids to buy this at 60 cents, 5 at 50 cents, 5 at 40 cents. On the sell side, there's 10 offers to sell this at 75 and 4 to sell it at 82. No trade would occur from this because the highest bid is 15 cents below the lowest ask, and that difference is called the bid-ask spread. And the bid-ask spreads in this market are actually very big. That's actually the lowest one, and that's 15 cents. Because the implication is that if you like, the true price, if that's a thing, lies somewhere between the bid and the ask. And if you have a very large bid-ask spread, then trying to figure out what that price is difficult. And in principle, if the market was working well, you'd be able to interpret the prices as exceedance probabilities, which means that they should monotonically decline as you go up to higher temperatures. Although there are a few, when you look at the last trading price, there are places where the actual price goes up and then before going back down. And this could all be explained really down to the fact that you had very low volume. If you looked at the number of contracts that were changing hands, it was very low. There was not that much trading occurring on this market. So it was very difficult to actually interpret these prices. Look, you have a bid-ask spread there. 0.3 is the highest bid and 80 is the lowest ask. That means the implied probability could be pretty much anything. Now, this market was suffering from a liquidity problem. And a lot of markets, prediction markets for specialized topics have suffered from this problem. When you run these markets for things like sports, entertainment, you tend to get a lot of activity, a lot of people, a lot of disagreement, and these markets are run by disagreement. They thrive on disagreement. So a lot of trading can occur and the markets actually work quite well. When people try to use these markets for specialized topics, like the temperature anomalies, they run into a problem of low activity. And ironically, that can happen if there's actually a broad consensus amongst the participants. So if everyone agrees essentially on if we ran a market for whether a fair coin is going to come up heads, nobody would be willing to buy that contract for more than 50, and no one would be willing to sell it for less than 50. So there'd be very little trading, even though there was a total consensus as to what the price should be. Another way of sort of putting this is that these markets, like the in-trade markets, are zero-sum markets. The gains, the rewards of the people who win, or people who get it right, maybe they're just lucky, but those people, by construction, have to come from the losses of the uninformed participants or the unlucky participants. And if uninformed participants don't show up, there's no reason for the informed participants to show up, because where are their winnings going to come from? They have no one to trade with. They have no one to trade against. In fact, a lot of these markets aren't just zero-sum, they're negative-sum, because the in-trade platform would take a commission. So you know that in total, if you take all the participants in total, they will come out of it with less money than they went into it. Now, you can address this problem by using a market maker. A market maker is just a participant who's in there and is always willing to trade. Now, lots of financial markets have market makers, and in fact, in regular gambling, you can think of the bookmaker as a market maker because they're willing to take bets on for all outcomes. But that market maker can also be subsidized, and this is where you completely deviate from the model of conventional gambling. So essentially, the market maker or the bookmaker wants to lose money to the participants in return for good information. But that's obviously a very different business model to the business model that conventional bookmakers use. And if you use a subsidized automated market maker, you can fix the liquidity problem because you now no longer have to attract uninformed participants. In a sense, the market maker steps in and plays the role of the uninformed participant. What you do need, of course, is someone to provide that subsidy, some organization or whatever who wants the information, who is prepared to provide that if you like, it's prize money. You're now putting prize money on the table for people to win by providing good information. So the market maker that we use in the markets that we've run is called the logarithmic market scoring rule market maker that was developed by the economist Robin Hanson. I won't go into if you look at the reference, if you're interested in the equations, it's there, but I can explain it graphically, that it's just an equation whereby the market maker can quote a price for, if you want to buy a contract for a particular outcome, the market maker will quote a price of that contract based on how many of that contract it has already sold compared to other contracts. And as it sells more and more of a particular contract relative to other contracts, the price will increase. And the amount the market maker makes by selling contracts is the area under the curve. So if you come to me and you want to buy 400 of a particular contract, the market maker will quote a price which is the area under this curve, the blue bit. And that's how much the market maker will receive from you to buy those contracts. If that contract corresponds to the thing that actually occurs, the market maker now has to pay you 400. It has to pay you the rectangle, which means the net loss of the market maker is the gray part of the curve. And because of the shape of the curve, the net loss of the market maker is bounded. So although the market maker will lose money if the forecast is good, the amount of money the market maker can lose is bounded. And what's particularly elegant about the logarithmic market scoring rule market maker is that it turns out that even if only one participant shows up, so let's say you're the only person who shows up to the market, and you just buy contracts, and I'm the market maker, and I adjust my prices, and I keep adjusting those prices until my prices match your probabilities, that is exactly the same as if you had just told me the probabilities, what you thought the probabilities were, and I rewarded you using the logarithmic scoring rule, which is a proper scoring rule that's widely used to evaluate probabilistic forecasts. Now, if there was only one participant, you could argue the easiest way to do it would be for that one participant just to tell me their probabilities and then I would reward them. But as soon as you have multiple participants, the market using the scoring rule doesn't just reward those participants in line with the logarithmic scoring rule, it also automatically aggregates their views into a collective consensus forecast. The other obstacle that prediction markets have faced is legal, because if you think that this looks a lot like gambling, then the regulators of gambling would agree with you. That if you have a pay-to-play market where people have to pay to take part, where they are actually betting their own money, that is classed as gambling. And in the US, gambling is regulated at the state level, and in a lot of states it's illegal. And even in the UK, you can run online gambling, but there's a lot of regulatory hassle you have to go through. You have to get various forms of gaming licenses and what have you. Now, the IEM, which is run by the University of Iowa, they actually have what's called a no-action letter from the US Commodity Futures and Trading Commission that says that so long as they keep the number of participants below a certain number and they keep the maximum stake below a certain amount of money, I think it's $200 or something like that, then the CFTC, which regulates futures markets, will leave them alone. Interestingly, there was another prediction market in the US called PredictIt until a few months ago when they had their no-action letter. They were affiliated with a university in New Zealand, and they had a no-action letter, but the CFTC pulled their no-action letter. I think that they believed that they were becoming, if you like, too commercial and looking too much like a commercial gambling site. In the UK, there's a website called Smarkets, which is essentially a commercial prediction market platform that's regulated by the UK Gambling Commission. Recently, the US has seen Kalshi, which is a commercial prediction market platform, but they're not regulated as gambling, they're regulated as a futures market, because in the US, the advantage of that is that regulation is federal, so you only have to deal with one regulator for the whole US rather than 50 different state regulators. So these gambling regulations, even in the UK, are a big obstacle to setting up prediction markets. But once you've decided that you're going to subsidize your prediction market, once you've decided that the people participating in the market are not supposed to be a source of revenue, but a source of information, then that actually frees you up from saying, well, actually, they don't have to pay to take part at all. And as soon as you've done that, most of this regulatory burden goes away. So none of the markets that we have run have involved people paying to take part. They've all been by invitation markets where people have been invited to take part based on their expertise, and then they get assigned on-platform credits to participate with, and then at the end of the market, those on-platform credits, how many they've accumulated, translate to some kind of financial reward. So to make things a bit more concrete, this is an example of a market to predict the number of hurricanes that would occur during 2020. And this market was sponsored by Lloyd's Lab, which is an InsurTech accelerator run by Lloyd's of London. And in the market, there were 21 distinct outcomes, ranging from no hurricanes to 20 or more hurricanes. And when about 20 people from academia and the private sector participated in this market, and at any time, the market maker would be quoting a price for each outcome based on its relative popularity. So for example, and these prices could be interpreted as probability. So for example, here, the implication is there's a 3% chance that there will be 14 hurricanes. And this market, and then when the actual outcome, the actual number of hurricanes was known at the end of the 2020 hurricane season, the contract corresponding to that number would be worth 1 credit, and all the other contracts would be worth 0 credits. So this market was actually opened in August 2020, which is during the hurricane season. That's not ideal, but that was because of the timing of this InsurTech program that Lloyd's of London run. As I mentioned, we had about 20 participants from different universities and some private companies taking part. And what you're looking at here is the median, essentially that distribution I just showed you, as it evolved in time, the median of that distribution in blue, and the 50% interval of that distribution in gray, and how it evolved in time from the end of August, when the market was opened, to the end of November, when the hurricane season runs from June to the end of November. And as I said, when we opened the market, 2 hurricanes had already occurred. We initialized the market with an average of 6 hurricanes, which is the climatological average. But as soon as the market opened, the median jumped to 9 hurricanes because people were already expecting it to be a particularly active season. And then during the season, as storms developed, became hurricanes or didn't become hurricanes, you can see how the consensus view of the market evolved over time and is then reflected in the prices, reflected in the evolution of that distribution. And in the end, there were 13 storms classed as hurricanes by the end of the season. What actually happened, the actual number, if you look it up now, it's 14 storms, but because one of the storms was upgraded, but it wasn't upgraded until the following year. And that does actually, that's an issue that arises in prediction markets, is you have to be very careful to define what the market's going to be settled on, because you get weird cases like that happening, and you have to decide what you do. So in this case, we just settled, the settlement was based on the number as of December, ignoring anything that happened after that. To give a sports analogy in sports betting, when Lance Armstrong was stripped of all his Tour de France titles because of the drug issue, bookmakers didn't have to sort of start refunding people and taking money off people who'd bet on Lance Armstrong, because that would just be too impractical. So at some point, you have to say the market will be settled on some official number as of some date, and any revision that happens after that date, we're not going to count, just for practical reasons. Now, the other third issue I spoke about was circularity. If we just ran a market for global temperature anomaly, like Mark Boslow's market, but we say we were running it for 30 years ahead, and let's say that we were running that market and it was working, but it was predicting a relatively small increase in temperature anomaly, we wouldn't know whether the market was telling us that they thought that the climate sensitivity was maybe lower than people think, or whether they were expecting draconian policies to reduce greenhouse gas emissions. And if you can't differentiate between those two interpretations, it's not that much use to policymakers. And so to tackle that problem, we envisage, well, if you have a two-dimensional market where perhaps instead of just having predicting the global temperature anomaly, you simultaneously predict the carbon dioxide concentration, let's say 30 years in the future, 40 years in the future. So you now have a joint outcome market where you have each of these squares in this grid is a different outcome. And then, if that market works, it'll give you an implied joint probability distribution. So you can get marginal distributions of the carbon dioxide concentration, marginal distributions for the temperature anomaly, and some implied information about a transient climate sensitivity. But that market has over 5,000 different outcomes, which is a huge number of different outcomes, far beyond the number of outcomes that prediction markets have been run with in the past. And so there was a question of, could a market like that actually function in reality? Could people actually participate in a market like that? And so to address that problem, back in 2018, when I was still at Winton set up a market with exactly that structure, but we didn't want to wait 30 years to settle the market. So we just relabeled the axes, monthly temperature for the UK and monthly rainfall for the UK, which are just two statistics that the Met Office publishes on their website. And we recruited a couple of dozen teams from British universities to take part in this market, and we ran 6 markets to predict these quantities for April through to September 2018. And what you're looking at here is an animation of the prices from the June market, from the time that the market opened in March 2018 until the end of June 2018. The black dots are just there for reference. They're the historical Junes. And the blue cross is where reality ended up. That June was actually, I think, the second warmest June on record. And what you're looking at is an animation of how the prices, so all of this activity is down to the trading of the participants. You'll see that the market captures the negative correlation between temperature and rainfall. You expect a hot summer to also be a dry summer. And you can also see how it converges on reality as time goes by, because as you get closer to the end of June, first of all, you can start using medium range weather forecast. And then obviously, once you get into June itself, you're actually accumulating numbers that are contributing to these statistics. And so you would hope that the market would converge on reality. And what these experiments showed was that these markets with very high numbers of outcomes can actually function, and that people can actually engage with them. Most of the people who are trading in these markets were trading programmatically using an API rather than through a user interface, because there's so many outcomes. The way that these were not pay-to-play markets. The teams that participated were given on-platform credits, and then at the end of the experiment, the 10 teams that had accumulated the most credits were given prize money. Their departments were given prize money by Winton Group. Okay. How accurate are market-based forecasts? So this is one I can sort of do my best to answer with the information that we have available so far. Over the last 5 years, we've run up 24 markets for climate-related risks. If you count the markets you just saw, there was 6 monthly markets, and if you count temperature and rainfall, if we treat them separately for the purposes of this exercise, so that's 12 markets right there. We've also run markets to predict sea surface temperatures in the tropical Pacific, which is an El Nino indicator. We've ran a market to predict UK wheat yields, and then we ran a couple of those hurricane markets that I just mentioned. So 24 markets, all of them producing probability distributions. So it's the issue of how do you evaluate probability distributions. So we can at least ask how well calibrated are these markets probabilistically, or as meteorologists would say, how reliable are they? So what you're looking at here, the blue line, is a plot of the Agora forecast and how often reality fell below each quantile of the forecast. So how often did the reality fall below the 20th percentile? How often did it fall below the 40th percentile? If you have a perfectly calibrated forecast, you'd expect it to fall below the 20th percentile 20% of the time, below the 40th percentile 40% of the time. So you'd expect to see a diagonal line if you had a huge number of forecasts. As soon as you start dealing with a finite number of forecasts, you will expect deviations from the diagonal. The gray envelope is the same thing. It's an envelope of calibration curves for perfectly calibrated forecasts that were constructed by sampling a synthetic reality from the forecast distribution. So those forecasts by construction are perfectly calibrated. So what the gray envelope is showing you is how much deviation would you expect from the diagonal for perfectly calibrated forecasts, given the fact that you only have 24 of them. The more forecasts you have, the tighter this gray envelope would be. So what we can say from this result, and similar results at different horizons, is that the forecast that we have produced with these prediction markets so far are consistent with perfectly calibrated forecasts, with a couple of caveats on that. The first caveat is that we only have 24 forecasts, so that's you'd like a bigger sample. We could get a bigger sample if we did these prediction markets for shorter horizons. If we did them for like 5-day ahead forecasts, we could collect a lot more data. But then that would make the second caveat worse, which is, okay, so these forecasts are calibrated out, but none of these forecasts had a horizon beyond a year. How sure can we be that this calibration would persist if we go out 5 years into the future, or 20 years, or whatever? And the answer to that is we don't know, and there is really no way of finding out unless we actually try it. But of course, that's not a caveat that's unique to forecasts produced with prediction markets. That's a caveat that applies to all long-range climate forecasting, and it's the bugbear of climate forecasting generally. So, to summarize, we contend that prediction markets can address these 3 problems of fragmentation, the multidisciplinarity of the field, the information asymmetry by essentially making people have skin in the game by rewarding them based on performance. You can at least filter out the people who know they don't know what they're doing. The circularity issue can be addressed using those joint outcome markets, and we've demonstrated that those joint outcome markets can actually work. And so our vision, if you like, is that prediction markets could become a mechanism for aggregating all of this climate expertise into consensus forecasts and also allocating climate research funds in a performance-based way. And that's particularly the second point is quite a radical departure, but we think that this is possibly one of the best use cases for scientific prediction markets that there is. Finally, I'd like to invite anyone who's interested in participating in one of these prediction markets to a demonstration market that we're going to launch next month. Actually, it's identical to the one I showed you for the 2020 Atlantic hurricanes. The only difference is that this time, we're going to start it long before the season starts to make the forecast horizon much longer. So it's to predict how many hurricanes there will be in the 2024 Atlantic hurricane season that runs from June through November 2024. Again, it won't be a pay-to-play invitation. We have a subsidy for the market, essentially a prize for the market of £20,000. And if you're interested in taking part, then you can register your interest at the cruciallab.net web address. So, and hopefully having it, now that I've explained how the 2020 market worked, I've made it a bit more tangible as to how this thing actually works. And so, yep, that's what my talk. I hope that if you have any questions, then you'll launch them straight at me. Thanks very much.